Starting with the introduction, the purpose of the lab is to calculate the mass of a black hole using the information on the orbit and the mass of the star orbiting the black hole, and then using the information on the mass of the black hole to calculate the required initial velocity of the spaceship that intends to leave the gravitational field of the black hole and the planet orbiting the black hole. The lab followed the following steps: calculating the mass of the black hole. In step 2, calculating the initial velocity of the spaceship so that it can escape the planet and the black hole. Result was mass of the black hole 1.44 e34 kilograms, and the initial velocity of the spaceship -6 e6, 1 e7, 0 meters per second. The models. These are the models created from the 2 steps. The model on the left is from part 1, and the model on the right is from part 2. For the model on the left, the green line shows the orbit of the star, and the arrows show the forces acting on the star. For the model on the right, the blue line shows the orbit of the planet, and the purple line shows the trajectory of the spaceship. The first main physics idea uses velocity and momentum. Velocity is the rate of change in an object's position with respect to the amount of time passed. Momentum is a vector quantity calculated by multiplying the mass and velocity of a system. And according to Newton's second law, the change of momentum divided by the change in time equals to the net force acting on the system. The second physics idea used is Newton's law of universal gravitation. And according to that, the gravitational force equals -g m1 m2 over r squared r hat. The third main physics idea is parallel and perpendicular forces, in which F net equals F parallel per F perpendicular. F parallel equals dp over dt times p hat, and F perpendicular equals p times dp hat over dt. Now to part 1. GlowScript's WebVPython program was used to create a computational model that could be used to calculate the mass of the black hole. Initial conditions were initial time 0 seconds, mass of the star 2.0 e 30 kilograms. Assumptions were delta t 36,400 seconds, which is 1 day in seconds, and gravitational constant 6.7 e -11, which is a gravitational constant that's rounded to 1 decimal point. Line 10 was changed for email address for randomization. Line 21 was for a change for the mass of the star. Line 124 was changed for delta t. Line 163 and 164 were changed for final initial momentum. Line 167, 168 were changed for the change in velocity and momentum. Line 74 was changed for the net force. Line 177 through 179 were changed for a parallel component of the change in momentum. Line 182 was changed for F net parallel. Line 185 was changed for a perpendicular component of the change in momentum. Line 188 was changed for F net perpendicular. Line 192 to 194 were changed for mass of the black hole. And finally, lines 202 to 208 were changed for the arrows that represent the net force and its parallel and perpendicular components. The part 1 results were mass of the black hole 1.44 e 34 kilograms, F net equals 8.87 e 28 newtons, F parallel equals 1.58 e 28 newtons, and F perpendicular 8.74 e 28 newtons. Now this is part 2. Once again, VPython was used to create a computational model that models the trajectory of a spaceship. Initial conditions that were provided were the mass of the ship, mass of the planet, initial time, black hole position, black hole radius, planet position, planet radius, and the maximum time was set to 7,500 seconds, as that was large enough for the planet to complete a full orbit, and the mass of the black hole was 1.44 e 34 kilograms, which was derived from part 1. Line 31 was changed for the mass of the black hole. Line 47 was changed for the maximum time, and line 61 and 62 were changed for velocity of the ship. Line 79 and line 80 were changed for the force by the black hole on the planet. Line 82 and 83 were changed for the force by the ship on the planet. Line 85 was changed for the net force on the planet. Line 93 and 94 were changed for the force by the black hole on the ship. Line 96 and 97 were changed for the force by the planet on the ship. And line 99 was changed for the net force on the ship. Part 2 results show that the ship successfully got away from the planet and the black hole. The time passed was 125 minutes, and the ship's distance from the black hole was 2.70 e 10 meters. Now to discussion. The possible room for error in part 1 was that delta t might not have been small enough, and part 2, delta t also not being small enough, guess and check method not being the most optimal, and the maximum t not being big enough, as a spaceship might end up coming back to the black hole later on. What does it mean? Despite the net force and its parallel and perpendicular components, and the change of momentum and its parallel and perpendicular components being equal to each other, the difference lies in the fact that while the net force and its parallel and perpendicular components are causes, the rate of change of momentum and its parallel and perpendicular forces are effects. What if, after multiple trials, a speed of -3.5 meters per second in the x direction and a speed of 1.7 meters per second in the y direction gave me a trajectory as close as possible to an orbit? The left shows how -3 E5 to the y direction, x direction, and 1 E7 to the y direction were input into the code, and the right shows how, the orbit of the spaceship and the planet. Now to conclusions. After creating a model to calculate the mass of the black hole and a model to calculate the initial velocity of a spacecraft, these are the findings. There has to be a force pulling the object towards the center of a kissing circle for the object to be in motion. And if the velocity is high enough, an object can escape the gravitational field of an object, even if the object is as massive as a black hole.